Next up, we have a talk from Olivia, who is going to be talking about macOS internals for threat detection engineers. So, round of applause for Olivia.
Hi, everyone. Hi. It's good we're running a little early because that allowed for problems. Yay. All right. Hi, everyone. Thank you so much for having me. My name is Olivia Gallucci, and today I'm going to walk you through macOS logging, how it intersects with some basic internals concepts like endpoint security, automation methods, and the transparency, consent, and control database, or TCC.db, and what that means in practice. I do want to say I've mentioned quite a few tools you already have seen today, specifically Mac Monitor. That is by pure coincidence because this tells a little bit of the story of how I learned about macOS internals. But yeah, I hope it just speaks to the quality of these tools. So yeah, let's start by discussing macOS and logging. So macOS's unified logging system was introduced in Sierra 10.12. It consolidates all OS and application logs into a single structured format. It's Apple's successor to syslog and ASL, and it documents everything from app crashes to process launches and entitlement checks. I can access it using log show and log stream, and I can filter it using predicates. Logs are written asynchronously, meaning not in real time, and buffered in memory before disk writes. So we don't usually use this for detection, but for context or correlation. One thing to note about ULS is that it is noisy. Additionally, the announcement of ULS was a big deal because it was not well documented and its design appeared to be mainly built for Apple's internal engineers. As a result, most people create or use tools to make ULS a little bit more accessible. Consolation is a tool that I use to make ULS accessible, and while Apple's built-in tools like Console and Log Show provide access to system logs, they're either too limited, overly verbose, or difficult to navigate. Consolation addresses this by offering a GUI that lets me filter, customize, and export data with far greater precision and clarity. It allows me to examine live logs and log archive bundles, set time ranges, and easily apply predicates for more granular searches. Additionally, it supports user-defined styles, so like yay, accessibility, and filtering logic, which helps extract the most relevant entries for whatever you're trying to search for. Both of these things are honestly quite cumbersome trying to use Apple's native tools. I use this tool along general reversing tools and other inspectors to help visualize and increase the visibility of findings. It also helps for things like presentations or when you want to visualize something to an audience as well. That said, there are a ton of macOS specific tools for visualizing and analyzing internals within the macOS research community. I have a few tables at the end containing a curated list of tools for reference. That said, macOS log collection, telemetry, and process monitoring are all closely tied to other macOS components like endpoint security or just ES. So ES is Apple's kernel event subscription API. The interface documents event process execution, file access, and memory mapping. At a high level, I think ES can be conceptually analogous to Linux's combination of LSM hooks and auditd or eBPF-based agents like Falco or Tracy. One advantage is that ESF events are structured as Swift native structs, so I can parse them and immediately enrich them with detection logic. The links in the footer are good examples of people doing this. It runs in userland and doesn't require a kernel extension, making it safer than legacy tools like OpenBSM and auditd, which are either deprecated or limited on macOS today. In short, unlike older mechanisms like auditd or OpenBSM, ES offers structured telemetry without needing a kernel extension. So this diagram shows the architecture and flow of how system extensions, Apple's replacement for kernel extensions, particularly the endpoint security extensions, bit into macOS across the user space, the system space, and the kernel. For reference, system extensions run in the user space for better security and stability, and there's three main types: driver kit extensions, network extensions, and endpoint security extensions. Each type communicates with the kernel through a well-controlled and restricted mechanism. This diagram can also show the trust chain, so like signing, activation, system daemons, and entitlements. Everything must line up in order for the endpoint security extension to work. And thus, using ES can be quite complex because it requires building and maintaining a privileged, properly signed system extension that processes high-volume events efficiently, which is why tools like Apple's eslogger exist, which is to simplify the event subscription, decoding, and logging for analysis and debugging. So eslogger is a command line tool built into macOS to query ES events in real time. That said, eslogger is still difficult to use because it generates an overwhelming volume of raw event data without sophisticated built-in filtering or easy integration for detection logic. It requires full disk access and special entitlements to function properly, and even then, handling its massive event output and maintaining stable, permission-compliant operations across macOS updates becomes quite challenging. If you're someone who could benefit from some experimentation and just seeing how this works, there's also some third-party apps. A notable one is the ESFPlayground by Jaron Bradley, which is a GUI-based tool used to test ES events with visual process trees. You'll have to use a separate application for that, but there's quite a few. And what you can do here is you can look at how you're building your detections and then understanding the system behavior underneath those. That said, now that we've covered endpoint security and logging, let's look at some macOS threats and how it intersects with logging and other macOS components. Many groups and individuals collect macOS-specific malware, but it's not always collaborative in terms of like the platform or the location, such as uploading to VX Underground or VirusTotal, right? One example of this is Objective-C's Mac malware catalog, which has a number of relevant threats that people have talked about even in the past couple days, such as stealers like Atomic Stealer, Coin Thief, Poseidon, and Meta. Each of these use various combinations of TTPs to persist and, at least in their mind, ideally operate undetected. So to push the research of TTPs, I use MITRE's macOS matrix. Anchoring the findings and a recognized standard strengthens the credibility of macOS threat intelligence. Like, it ensures that people recognize what some of the threats and risks are surrounding macOS. And it also ensures that the risk discussions are framed in an industry-accepted context. Using a shared language helps accelerate these behavior mappings, and at least in my experience, drives more effective cross-domain, cross-team, and even cross-company collaboration. So diving into one of these categories, we want to understand how malware persists on Mac. The most commonly abused vectors include plist-based launch agents, for example, fakeupdater.plist. These are auto-run and are incredibly common in Mac malware. For reference, a plist or property list is an XML formatted file used to store structured data like settings or configs for apps and processes, including auto-run services like LaunchAgents. Another example is LoginItem abuse. These allow apps to launch on login, often without the user's explicit approval. This is frequently under-monitored due to limited surface telemetry. Essentially, the system telemetry often lacks visibility into who added them, when they were added, or whether the user approved them, making persistence detection quite difficult without any sort of enhanced logging or third-party tool. Newer macOS versions, which really just means Ventura and later, offer some visibility into login items via system settings, showing the open@login apps and background items, but this is superficial and lacks historical logging or deep monitoring, making it insufficient for serious threat detection without an EDR or some sort of custom logging. Additionally, TCC doesn't necessarily govern everything that has to do with this, so the user approval often isn't required. For example, user-level launch agents are more commonly abused by Mac malware than launch daemons because they require no root or admin privileges when dropped into /library/launch agents. They run within the user's context and have GUI access, making them effective for phishing dialogues and some kinds of data theft. In contrast, launch daemons reside in /library/launch daemons, require root privileges to install, and run at system boot. They also persist across all of the users, and these essentially just provide a more powerful form of persistence. And at the same time, they're less frequently abused and are typically favored by threat actors that have already obtained advanced privileges. Advanced, like more like elevated. So yeah. For reference, the TCC.db is a framework developed by Apple to manage access to sensitive user services and data on macOS. The primary goal of TCC is to give users transparency regarding how their data is accessed and used by applications. As mentioned, the TCC.db is a database that lives on disk, and there's multiple on each operating system. So like one per each user, and then one stored at the root level. One of the primary differences between these two databases is that system-wide permissions, like full disk access, are only stored at the system-level database because they affect all users, require an admin password to change, and are recorded in the root library database. TCC.db governs permissions decisions for things like system and kernel extensions, automation tools like LaunchAgents, LoginItems, and apps, ensuring that any access to sensitive user data or privileged system operations complies with the user-approved security and privacy settings. It works alongside the unified logging system by recording permissions decisions at the database while logging related access attempts, prompts, and even errors in the ULS for system auditing and troubleshooting. To learn more about TCC.db on Mac and how to interact with it, I highly recommend Mint by the Eclectic Lights Company, which helps me collect information about my Mac and their permission flow within inter-process communication logs. Now, to get back to the abuse vectors, both of these examples, LaunchAgents and LoginItems, are types of plist abuse, which involves manipulating or creating property list files such as those used by LaunchAgents, LaunchDaemons, LoginItems, and login/logout hooks to achieve persistent code execution during boot or user login, often bypassing explicit user visibility or leveraging system services like LaunchD. So many malwares try to leverage macOS's trusted automation mechanisms to embed itself into normal system behavior. For example, XCSSET abuses Xcode projects by planting LaunchAgents inside developer environments, triggering automatic code execution during app builds and launches. CloudMensis abuses Safari and LaunchAgents to persist spyware components, allowing for the exfiltration and control even after reboots. Schleyer uses system scripts to create LaunchAgents, automating the download and installation of payloads without much user interaction. And as you can see, these automations are a big problem because it's what makes macOS so seamless, yet it can cause actual security risks. A particular cause for concern, well, automation concern especially, is osascript and how it interacts with things like inflow stealers. So osascript is macOS's bridge between the terminal and the GUI. It's the CLI wrapper for AppleScript, JavaScript for automation, and other osascripts. This tool allows scripts to interact with apps like Finder, Safari, and system events without elevated privileges. And while powerful for automation, this trust and access to user interfaces makes it ripe for abuse by malware like Amos. So execution begins when the CLI is used to run a script. The text is parsed by the OSA runtime and then is dispatched as an Apple event to the appropriate app or system service. The point is that the entire execution path is run as the user and not root. So macOS prompts for password entry are not trusted, or no, are trusted by users and are usually ignored by security tools unless they're inspected deeply. Amos weaponizes osascript for social engineering, so it will execute an Apple script that creates a legitimate-looking dialog box with a prompt for a password entry. These prompts mimic macOS's system alerts, and because they're not exploits, but social engineering, they bypass things like Gatekeeper, some antiviruses, and even sandboxes. Additionally, they can blend in because they can call native icons, default buttons, and even system sounds. So here's a deobfuscated command used in a mid-2024 campaign. This specific string was decoded at runtime from a base 32 blob. It creates a dialog box that says system update required with a password prompt. When the user submits input, Amos logs it and sends it off via HTTPS to a C2 server. These strings are rarely visible statically due to the encoding and then the memory layer decoding. So right here you can see that Amos is trying to use runtime decoding to then evade static analysis. This assembly snippet shows part of an ARM64 loop. It loads a byte, it XORs it, and then it stores it back. This looped function is then used over 100 times within a single binary to decode the strings, including the AppleScript used on the previous slide. The decoded string is then passed to system for execution, ensuring that the malicious logic never exists plain text on disk. This is where we need to shift gears. Given the amount of various osascript commands linked to Amos alone, signature-based detections won't always help. The use of specific AppleScript phrases, high entropy and command line arguments, abnormal parent processes like an unsigned installer, and then the timing correlation between the password prompts and the outbound network activity. And these are all just suggestions. You might not want to use them all together. So essentially, you want a pipeline that will correlate these layers to flag real info stealer or malware usage. So how do we fix this? So this is a basic rule triggering when osascript is called with a display dialog and a hidden answer. That's low-hanging fruit, and you can enrich this with any sort of detection logic, such as entropy scoring, parent binary signatures, and post-exec network events. There's also tons of other techniques, rules, and information that have been documented for Amos and similar info stealers. Luckily, people have actually recorded these techniques and even their frequency for specific malwares, including Amos. For example, here is some Amos data from Red Canary. So speaking of Red Canary, I know Brandon just presented, and he's open sourcing like the second version of this. But yeah, their open source Mac monitor tool, and if you want the POSIX atomic test harnesses, provide a way to illustrate and understand logging, macOS internals, and the ES, as well as malware behavior if you're running them concurrently, like Amos. So Mac Monitor collects and visualizes ES telemetry, helping me see the detailed events like process launches, file activity, and inter-process communication. It helps connect what kinds of raw telemetry macOS makes available and how activities are then reflected at the system level. Meanwhile, the POSIX atomic test harnesses are just a suite of like Python-based tests to simulate many variations of MITRE attack techniques. And one thing to note is that like you don't actually have to use the Red Canary ones. You can make your own or just find other open source ones online to run as well. The point is that these harnesses try to just allow for simulated attacks on macOS, helping validate whether or not whatever you're trying to change or monitor or detect is actually working. Unlike traditional atomic tests, which are supposed to just have like very similar attack behaviors, their tests in particular try to run and test by offering a programmable exploration of a bunch of different ways a specific technique could be executed. And then by running these harnesses while Mac Monitor is running, it will show exactly which ES events are then generated, what binaries are loaded into memory, and then how different forms of execution, such as like command line scripts versus an applet, might trigger different results in telemetry. Specifically, when looking at malware like Atomic Stealer, these tools become even more valuable. So like Amos uses AppleScript, JavaScript for automation, and others in various versions to steal credentials and information. By using the harnesses to emulate these behaviors or just running the behaviors manually, you can, and then also using Mac Monitor to review it, you can then see what is happening on that device. And those events can then be used to try to detect such behavior or figure out where the detection gaps on the device exist. So with that foundation in place, let's step back to logging and summarize the internals and system behaviors we've learned today. So we examined the unified logging system, which asynchronously captures structured OS and application events in real time. And then we also examined endpoint security, which provides real-time Swift native event streams without requiring a kernel extension. We discussed automation artifacts, so like LaunchAgent, LoginItems, osascripts, andplists as common persistence and execution mechanisms tied to user land processes and LaunchD behavior. We explored the TCC.db, which enforces privacy controls at the database layer, mediating access between sensitive services while exposing permission state through both user and system level records. We highlighted how independent threat intelligence, including Objective-C's malware catalog and MITRE's macOS matrix, provides structure to tracking abuse patterns like those seen with info stealers such as Amos. And then lastly, we covered tools like Constellation, ESF-Playground, Mint, and Mac Monitor to make the learning and analysis of these topics a little bit easier. So where do we go from here? So all citations are included in the slide footers and images. If you want to get involved, you're already here. So that's great. There's also an amazing conference and program called Objective for the We, which is how I attended last year's conference and the conference in Ukraine. If you're interested in my other work, I have some presentations coming up in the next few months, as well as some online. And all of my presentations or written work are available online. I actually have a blog post on this topic, macOS internals for detection engineers, but it takes a different approach, focusing more on the internals themselves rather than the accessibility and learning about them. So some presentations are being moved to the newsletter page. Last month, I started a newsletter called Return to Read, or RET to Read, which is about macOS security and OS internals. So yeah, thank you so much for providing me the opportunity to present. I'm really grateful to be here. And I think everyone that knows me knows this, but OBTS really helped build my career and network. I'm very grateful to Andy and Patrick, who have given me so many opportunities, as well as so many others, to help them thrive in the Apple security space. Lastly, if you're a student scholar, I'd encourage you to think about speaking next year, and I bet you'll be pinged about that soon. Oh wait, I do have one more note. I really want to thank Christine and Stuart for helping me in the speaker mentorship program. I learned a lot, and I'm really excited to see where that program goes. So yeah. Ooh.